Back, we're going to continue our look at the wave equation, wave propagation. We're going to continue looking at an elastic string. This time, last time we had two fixed ends. This time we're going to have a fixed and a free end on our string. So our boundary condition would be our fixed end, right? This is placement 0. We have a non-fixed end. So, well, what does that mean, non-fixed? Well, that means the wave isn't going to end at the end of the rod. This is kind of like the heat equation. Remember how when we had an insulated end, where you have like where the heat couldn't escape the rod. It doesn't just stop, right? It can't just dissipate right out of the end. It can't. It's insulated. So it's always going to increase. So what's going to happen with this end of the string, is the wave is going to propagate right through the end, right? It's not going to just dissipate right off the end there, because it can move freely. So what we're going to write, the way we're going to write that is as a derivative at the length. This end is not fixed, right? So you can think of it like it's not causing any change in the wave's behavior because it's free. So no change in the wave behavior. That's the way I like to think of it. Whoa. Okay. I'm not writing out that whole f of x, but you can see it's not as bad as it looks. Okay? Because you can see two of them are 0 on two of the intervals. Then we have 1 for the middle interval, so it's really not that bad of a piecewise function. Not like the last problem. But yeah, that's the that's the position initial condition. What does it give us for no initial velocity? Okay. No initial velocity, so u of t x0 is 0, initial position u of x0 is f of x. This being our f of x right here. We know how to separate the variables, right? Step 1, separate. Well, I can do it again really quick. We have alpha squared. We plug in ux. What is the wave equation again? Right, heat equation, but with one extra t on the end. That's how you remember it. This gets plugged in for that one. This gets plugged in for that one, right? We know how to do this. We should be pros at separating the variables by now. If you're not, you got to go back and practice that. Remember, I used positive lambda for my definitions here. So here's our two ODEs, second order ODEs. We have boundary conditions for x, so we use x for our boundary value problem. We have x of 0 is 0, x of L, well, not exactly. We have x of 0 is 0. We have x prime of L is 0, I believe. Yeah. So, and the equation was it's right there. This. So let's go ahead. Start with greater than 0. We should be experts at boundary value problems as well by now. Write the general solution. E to the mu x plus C2 e to the negative mu x. We also need x prime, so mu C1 e to the mu x minus C2 e to the negative mu x. Boundary condition number 1. Right, see how I got to right to there? If x is 0, we're left with mu C1 minus mu C2. The mu's cancel out. C1 is equal to C2. Wait, isn't it just equal to C2? Oh, wait, no, not x prime. Just x. Yeah, C1 plus C2 equals 0. C1 equals negative C2. So then x is equal to negative C2. I'm just plugging in for C1. Mu x plus C2 e to the negative mu x. You can already see this is only trivial because take out a C2. Well, let's just, you don't even have to do that. What value of mu makes this 0? Well, if this is 1, and this is 1, then it will be 0. So if mu is 0, then let's look up here. If mu is 0, then we're left with x equals C1 plus C2. We know C1 is equal to negative C2. So then we know it's only trivial solutions, which we don't want. So let's continue on to lambda equals 0. We know this is our reduction of order case, right? We can now find x prime because we're going to need that. First condition, C1 is 0. Second condition, wait, did I do the second condition for this one? Of course, I oh boy. What am I doing? Wait. I got ahead of myself. So sorry. That's going to confuse a lot of people, isn't it? Oh boy. Ignore this little bit I have here. I'm just going to kind of go from here to here. When I say here, I mean here to here. Okay, so prime of L. Let's look at x prime. Of L, C1 is equal to negative C2, so that's mu, come on, mu C0 negative C2 e to the L, or mu L, plus C plus mu C2, I guess it would be minus. What would make that 0? Well, if mu is 0, then that's going to be mu C2 minus mu C2, which is negative 2 mu C2. Mu is going to be 0. Once again, if mu is 0, we end up with this. It leads to the same exact answer. Only trivial. Right. Okay. This one. Where was I? X prime of L. XC sub, no, this is just going to be C2 equals 0. Well, because C2 times L equals 0, C2 equals 0. X is only trivial. X is only trivial. Next. Less than 0. And, that leaves us with negative mu squared. So then I just know from memory that's complex. Then we solve the characteristic and then you just write the general solution. This is with Euler's equation for complex second order ODEs. That's the shortcut. Yeah, take the first derivative. Actually, we don't even need to take the first derivative until after the second one. So let me just go. Yeah, make our life easier. Let's just C1 equals 0. then we could take the first derivative, because then we're just going to be mu c2 cosine. Because I've taken the derivative of that sine term. X prime of L. That's a much better way of doing it. I should have did that before. Mu c2 cosine mu L equals 0. What makes mu L, what makes cosine equal to 0? Cosine of anything with n minus 1/2 pi, right? Remember that? Check out my even and odd video, or whatever. Yeah, that's always going to make a 0 value for cosine. Remember, any cosine, like value like pi over 2 is 0. So like say n is 1, this would be pi over 2. Cosine pi over 2 is 0, and so on and so forth. Mu would be, like, you can rewrite this actually. I prefer to write it as 2n minus 1 over 2 times pi, and it's pi times L, so it's oh no, divided by L. So it's going to be all this times pi divided by L. So then our eigenvalue, eigenfunction, eigenvalue would be, it's negative, so negative 2n minus 1 squared pi squared over 4l squared. Eigenfunction x to the n, we were left with c1 is 0, so c2 sine, so it's cn sine of 2n minus 1 times pi over 2l times x. Little x, right? Now step 3. Solve for t. Might as well just go down to the next page. Okay. Do I remember what the t equation was? Of course I do. Well, I remember, I'm going to move over to the right side, so it's minus alpha. Remember, it was alpha, lambda. So it's just alpha squared times lambda times little t. So it's alpha squared times, so this is negative 2m minus 1. I'm just going to rewrite lambda times alpha squared times t. Oh, I forgot the pi squared from lambda times t. This is second order. So then we just solve the characteristic equation. This is imaginary. It has to be imaginary. It always has to be imaginary, else we would not have a Fourier series, right? Excuse me. Well, actually, you'll find out when we do Laplace. The next section, we're not going to have imaginary. And we have to deal with hyperbolic trig functions, right? We'll get to there. C1 cosine 2n minus 1 pi alpha t over 2l plus C2 sine, same thing on the inside. Wait, 2l? Oh yeah. It's pi alpha t. Step 4, fundamental set of solutions and the general solution. So un of x of t is going to be, well, we have c sub n. Once again, I'm going to use the same notation that I did in the last video when I'm going to use c and d. So when I multiply all these constants together with the cn that's up here, they're going to become C and D. So C1, C2 times Cn is going to become Cn and Dn. They're both new constants, even though I'm calling one of them C. I just want to stay consistent with my notes. So we have Cn cosine. All I'm doing is multiplying t and x together. 2n minus 1 pi alpha t over 2l plus d sub n sine 2n minus 1 over 2l pi alpha t, and then we just have that other component from x, which multiplies everything by sine of 2n minus 1 over 2l times pi times x. So then the general solution uxt is sum n equals 1 to infinity Cn cosine 2n minus 1 pi alpha t over 2l plus d sub n sine, man, this is long, 2n minus 1 pi alpha t over 2l, all multiplied by, oh man, sine 2n minus 1 pi x over 2l. Fantastic. U of t, xt is n equals 1 to infinity. It's all the same. I gotta write this all down again. Holy crap. Oh man. Oh, that's rough. Oh, that's rough. That's gonna be what? Negative sine 2n minus, 2l over 2n minus 1 pi alpha t sine 2n minus 1 pi alpha t over 2l times c sub n. This would be plus. Times, this doesn't change. Step 5. Okay, I just looked at the integration, not too bad. Step 5, initial condition and Fourier series. Ux0 is f of x, which, remember, we're only going to look at the one case, really, but should keep it as f of x for now. If we make t0, this goes away, this goes to 0, this goes to 0, this goes to 1, we're left with this. Wait. Excuse me. I just realized these t's don't move down here. I made a grave mistake. See what I mean? That t is part of the inside of the sign. You know what I mean? Those t's don't go there. Okay, alright, that makes more sense. So we're actually left with cosine of 0 is 1, so then we're left with this whole 2L over excuse me. Well, actually, I'm looking at you. I should be looking up here at this one. T 0, then this goes to 1, so it's a C of n times this. Alright, that's it. Now for u of t, which is the one that I was looking at by accident. We know that one's 0, because the velocity was 0. I know this term goes to 0, so then we're left with d sub n times that whole thing. Alright, that cosine goes to 1, so it's d sub n times 2L over... Oh, I did it backwards in my notes. Oh no. It's only the end of the recording though, so hopefully this stitches together okay. God, crap. Okay. Let me think. This would become... Oh, I lost my train of thought because I had to restart the recording. Yeah, d sub n times 2n minus 1 times pi alpha times sine pi x over 2L. Okay. That's it. But now you can see here, this one doesn't matter anyways. We don't need it because it's going to be 0. Because they give us this nice initial velocity of 0. Obviously, of course, if you were going to, solve it, if it was non-zero, then, you have to integrate it with that. Move this. You want to solve for this in your integral. This set's equal to the integral f of x, this times, not that, but sine of, n pi over L x. But we don't have to worry about it in this case. D sub n is 0. We do have to solve for C sub n. C sub n is equal to 2 over L. Now, these are some weird bounds. L plus 2, L over 2 minus 1, plus 1 on the top. Okay. Yeah, this is going to be an interesting one. This is a rough integral. Only if you're good at trig is it easy, I would say. That becomes 2L times 2, 4L over L cancels. 2n minus 1 times pi times negative cosine. The inside stays the same. Let's write that out. That's 2n minus 1 pi times x. So divided by 2, this will make that 4. And then times L cancels out. We have plus 2n minus 1 times pi. This is just the one case over 2L. Easy enough. Then we have plus cosine. It's the same thing but minus 1. Oh wait, minus minus is a plus, yeah. Okay, we're good. 2n minus 1 times pi over 4. This is minus instead. Now, I'm going to write something down here. You know what I'm talking about yet? Do you see the trig identity that we can use? Remember these identities? The sum? So I think they're called the sum identities. I don't know. Remember we have cosine a plus b. Now let me do this in a different color. Cosine a. I'm going to use shorthand notation. Cosine a, cosine b, minus sine a, sine b. If you ever take higher level mathematics or engineering courses, you'll see professors will start to use this notation. Mathematicians will be very angry. You know what? You're right. I'm doing mathematician videos. I'll stop being lazy. We're doing math here. This is beautiful stuff. A, what is this one? Oh, wait, minus b? Yeah, so there's a reason why I'm writing all these out. Sine of a, sine b, negative cosine a plus, oh, wait. This is all we need for now. So if you look at this here, we have a cosine of a plus b and a cosine of a minus b. So we have to solve for cosine of a plus b cosine of a minus b minus cosine of a plus b. So we have to solve for that. So using these two that we wrote down here, excuse me, we want that is equal to, well, first of all, if we do that, these two are going to cancel because it's that minus that. Then we're just left with 2 sine a, sine b. So that's pretty simple. So then, using that logic, c sub n is multiplied by 2, 8 over 2n minus 1 pi, times sine of a, 2n minus 1 pi over 4, times sine 2n minus 1 pi over 2l. Did it give us a length for this problem? No, just L. Okay. So then u of xt is going to be infinity. What is it? C to the n. So pull out the 8 over pi. We can. I'm trying to write it like this. And then we get sine 2n minus 1 pi over 4 times sine 2n minus 1 pi over 2l times what else is left? This is for x. We're plugging for Stevens. We have a cosine and then a sine. Cosine is pi alpha t over 2l. and the other one's just the pi x one. So that's just the sine 2n minus 1 pi x over L, 2L. So that should be the full answer. Yep. So that wasn't a bad problem, although the answer is kind of long, but it's not a bad problem. Can this be simplified? Maybe, but that's going to be kind of complex. To simplify this, just leave it as is. It's fine. A computer program will know what it is, right? This is the end for the wave equation, I guess. I mean, I could do a full Neumann problem example, but it's really the only thing that's going to change is the boundary value problem. And we've already seen cases like that with a heat equation. It would be the same thing. So like it doesn't really matter. So it's literally the same process as the heat equation. There's no difference. We don't have to worry about steady state for the wave equation, obviously, because eventually the only thing that's going to happen is it doesn't matter, because in heat the temperature can reach anything. With a string, the wave is only going to end up being at zero, right? It's just going to go back to equilibrium, which is at zero. There's no velocity, no position change. There's no steady. You don't have to worry about steady state. It's just zero for this problem, for the wave equation. For this particular case with the string, of course. So next, we're actually going to look at Laplace equation, which is more in-depth heat equation stuff, I guess. It's instead of it being on a rod, it's going to be on we're going to do a rectangular boundary and then a circular boundary instead of a rod. So it's like a rectangular rod, it's like 4 rods put together, and then we're going to have one continuous rod that's circular. So for the rectangle, we'll treat each side as a boundary. Well, kind of. It's kind of weird. I'll show you what I mean when we get to there. But for now, hope you learned a lot about the wave equation. There's also one more thing about the wave equation. If you have time, look up the Dirichlet solution to the wave equation. It's called Dirichlet. I think I spelled it right. I might do a video on this, but I've kind of ran out of time for the summer to make a video on it. But it's a useful solution to easily solve the wave equation. So you can check that out if you want to. Maybe show off to your professor that you know it. Just some food for thought. But I'll see you in the next section for Laplace's equation.